So welcome back. We just talked about that basically a precise solution to program analysis problems is impossible, but we want to have a way of computing program analysis solutions that are approximative. So they give you sound approximations of the analysis that otherwise you would like to obtain if you were to be able to compute it. So they should approximate this MOP solution that we unfortunately cannot compute because it's undecidable. And fortunately, by now, and actually since a few decades, we know how to do this. So there was a highly influential paper by these people that you see here on the top of the slide, Kem and Ullman, in 1977. That actually describes so-called monotone data flow analysis frameworks. And the idea behind this is really that it is a conceptual framework. So, it's not a framework like you're used to from programming, right? So it's not an application framework, it's a conceptual framework, but it is a framework because it essentially gives you a uniform evaluation algorithm. And then you can instantiate that framework with a number of different parameters. So for instance, with what we will call flow functions and some initial values and so on. And there are a few more of these parameters that you need to instantiate. But then as you do this, you obtain one particular, in this case, intra-procedural static analysis. And you will have some guarantees with that. So you will have the guarantee that this actually terminates at some point. You will have the guarantee that you get a sound approximation, and that is very nice. So basically, if you stick to this recipe, then you're guaranteed to get a sensible static analysis. So let's talk a bit more about these parameters or extension points that this framework has. And there's actually 5 to them. So first of all, you will have to decide whether the analysis should be executed on the control flow graph in a forward or backward manner. So are we talking about a forward or backward analysis? And that's just a Boolean value, basically. Then also we need to determine what is the so-called domain for the analysis information. So in the previous example that I showed you with the constant propagation, you saw that I had these environments, right? So they were mapping variables to numbers. And that could be one example domain of analysis information. So that's mapping type basically would then be the so-called domain. Then, of course, we have to somehow decide which effect a certain statement has on the information that we propagate through the program. And that's typically described as a set of functions, and they are called flow functions. And we will still be talking extensively about them. So essentially, every statement in your program, or here, every statement in the procedure, will be assigned a certain flow function that describes the effect that that statement has on values taken from the domain. Then also I already showed you that there are so-called control flow merge points. So whenever control flow merges due to branching, we also have to merge analysis information. And this is basically a binary operator on sets of values also taken from the domain. So we will get values from the left-hand side of the branch and from the right-hand side, and the output will be a single merged value. Then another question is how to initialize the analysis. So in the example I showed you, we had this vector where we initialized everything to 0, and that made sense in that example, but depending on the particular analysis you're doing, that might also look quite differently. And in general, these are values taken from the domain, but these values actually form a so-called lattice. And we will still be talking about this quite extensively. So the lattice essentially defines the elements of the domain, but it also defines how you can merge elements of this domain to other values. And by sort of insisting that these values and their merge operations, they form a so-called lattice, we can actually in the end have a mechanism that ensures soundness and that also ensures termination. That's why we have this restriction. And I'll still be talking quite extensively about this in the next couple of videos. So let's talk about a few of these steps in a bit more detail. So the first decision we had to make was whether we want to do a forward or backward analysis. And let's look a little bit about how we can make that determination. So in general, you can say that forward analysis, they tend to compute information about the past. And then also you can have backward analysis that compute information about the future. And we already saw this example here, right? Where we wanted to do constant propagation. And if you have a constant propagation, you want to determine or you want to have an answer to the question, which value does a variable carry? And you can think a little bit about this, right? So does this require information about the future or information about the past? Well, it basically requires information about the past, right? We want to know what have been previous assignments to this variable because that determines what value this variable carries. So this will have to be a forward analysis. Then another question is live variables analysis. So like I already said, this determines which variables will still be used later on in the program. Well, naturally, that is actually a question about the future, right? So we are here contemplating about future uses of that variable. So naturally, that will be a backward analysis. If you do a type state analysis, you will address questions such as, will this file handle be properly closed before the program terminates, for instance? If you ask the question that way, that will actually also be a backward analysis, right? Type state analysis can also make sense in a forward fashion, but actually there can be situations where you also do require a backward analysis. I won't be talking about this too extensively here. If you're really interested in that topic, I encourage you to actually read my PhD thesis that had a little bit about this in it. Then there can also be possibly defined variables. So that's something, like I showed you, for instance, also some IDEs are telling you when you're actually typing your code, so has a variable already been defined or not? And that would actually also then be a forward analysis, right? Because similar to a constant propagation, we worry about previous assignments to that very variable. Interestingly, sometimes it can be hard to tell because sometimes you can also have situations where forward and backward analysis can make sense. For instance, in security, a very popular kind of analysis is so-called taint analysis. And that lets you decide, for instance, such properties here, given such a program, can the value P2 that you see here, which is actually being printed by that program, can that actually carry the secret password up here? Obviously it can in this program, right? But if you ask the question this way, then you're basically making this statement your focus of attention, and you're interested in information about the past. So if you think about it that way, then your taint analysis would have to be implemented in a forward fashion. But you can also ask this question the other way around, focusing on this password and what happens to it. And you can ask the question, can the password actually be printed in the future? And if you ask about it that way, then you will actually be interested in doing a backward analysis. And actually both can make sense. So in particular, taint analysis is often being used to decide confidentiality properties. So these are rather of this kind, right? So here you're interested in figuring out what's happening to a certain value. But then also it's often being used for integrity properties. So here you are rather focusing on certain security critical APIs, such as this one that prints a potentially secret value. And then you are interested in what parameters is this being called with. And then you're looking at it the other way around. And there have been many type state analysis that are forward. There have been some that are backward. And sometimes you will even see, taint analysis. And sometimes you will even see taint analysis that combine both directions. And all of this can make sense depending on your particular program, the particular kind of property you're looking at. It can all have pros and cons. Okay, I've shown you how to conduct forward analysis, and that might seem very natural to you, right? So you basically just follow the control flow of the program. But it is an interesting question how to actually conduct and implement backward analysis. And if you want to perform a backward analysis over this control flow graph, for instance, then conceptually it's actually really simple, because you can simply perform a forward analysis over the reversed graph. So what you see here is the reversed graph where I've simply flipped every single control flow graph edge, right? So the control flow, for instance, is now not flowing anymore from this assignment to the print statement, but the other way around. And we've simply flipped every edge individually, so you get this reversed graph. And now you can simply perform a forward analysis over this graph here, right? So now this is your initial starting node of the control flow graph for this program. And you simply propagate along here, then along there, and so on, right? And so it's basically a forward analysis just on the reversed control flow graph. What's interesting now is also from an implementation point of view in particular, in a regular procedure, you may have situations such as this, where within a loop, for instance, you have an early exit, right? So you have a statement that says, if a condition is true, then you continue or you return or something like that. And here, for instance, we have such an early return. So that means in such a regular control flow graph, you can have multiple exit statements, and they are also called tails, sometimes a tail of a graph. And then when you do a backward analysis by reversing this graph, it means that this reversed graph can actually have multiple heads, right? So now we have multiple entry statements to that graph. And I'm telling you this because if you look at individual representations, like we have them in Gimple, for instance, in Suit, you will actually see that the implementation of the control flow, of the data flow analysis that we have there, it's actually accepting such graph representations that can have multiple entry statements, like you see here. And now you understand why that makes sense, right? So normally, if you think about it, a procedure always has a single unique first statement. But if you turn it around, like you see here, that's no longer the case. Now, the next point I want to talk about is this static analysis abstraction, or often it's also called domain. And I also told you already that typically this is meant to form a so-called lattice. So let's talk a little bit more about these elements that we are propagating through the programs and what properties they need for us to get a sound approximation and for the analysis to terminate. Well, the concrete lattice, it really heavily depends on the problem you seek to solve. So let's again look at this very simple control flow graph of a very simple example program. And here it's doing a bit of numeric assignment. It's also assigning some object values here. And eventually it's also doing some procedure call, okay? So that means it's interesting for a number of different analyses that you could do on this kind of code. For instance, let's first assume we're doing some constant propagation again, right? Then in this case, we are again answering this question: what is the constant value of some variable x at a given location, for instance, right? And here, like you already saw, we are having these mappings from variables two potentially, or in this case, actually definitely constant values, right? So a mapping from a variable to an integer, or could also be a real value, for instance, okay? But then we could also be interested in doing a so-called nullness analysis for this program. So this is asking the question or answering the question, which variable is actually null here at a given statement. And initially nothing, we assume that nothing is null, for instance, right? Or at least we don't know for sure what is null. But then here O has been assigned a null value. So here we could use, for instance, simply the variable name O to represent the piece of information that we now definitely know that O is null at this point. And then down here, this is being cleared again, right? So here the domain would be very simple. It would be simpler compared to the case in the constant propagation, because here we don't actually have a mapping. We have a set that sort of represents an implicit mapping, right? So it's basically saying if O is in the set, it implicitly means that O is being mapped to null. But we can even think about a so-called type analysis, right? So we have already seen type analysis before, but here we are reasoning about flow-sensitive type analysis. That's actually looking not only at what particular declared type a variable could have, but even what runtime type it could have. So what type of object has a variable actually been assigned at a given statement. And initially, we wouldn't know anything about O, which is the only reference type variable in this program. But here we do know something about O, namely that it's actually pointing to a null typed object, right? Or it's basically no object at all, but we are representing this by this null type constant. And then here it's actually pointing to an object of type O, big O, right? So here we would have this mapping, small o to big O, to represent that, right? So we would have a mapping in general from variable names to type identifiers. And very often you will see that lattices comprise sets of something that is then also called a power set lattice, right? So your individual lattice elements are sets. And then also very frequently these sets, they actually represent mappings or environments, but that does not always have to be the case. So there are exceptions in few cases. I've also implemented these exceptional cases in the past, but in, I would say, 95% of the cases, you're actually looking at sets of some elements. And then often these sets, they are used to encode mappings, and these are actually very frequently mappings, like you saw here, from static structures to something that is more semantic, so something that the program actually computes. So like I showed you here on the previous slides, for instance, here on the right-hand side, this type O, it's a type that is being instantiated at runtime, right? So this is something that is being decided at runtime, what particular type is actually being created here. So this is runtime information, but this variable identifier O that is static, right? Just by looking at the code and even just looking at the particular statement, we can always know what the name of this variable is. Similarly, from where we looked at this constant propagation here, on the right-hand side, we had a computed runtime value. Here you could argue, okay, just by looking at it, it's also static, right? But as I showed you earlier, this could have been computed by some numeric operation, right? And then we wouldn't know about it statically. We would have to evaluate it, sort of simulate the runtime effect in order to know what that value is. So I would argue it's still a semantic runtime value. But the left-hand side, the A, is certainly static. It's known ahead of time. That's what I wanted to get at. Okay, so accepting that we have the situation, right, then the next point I want to make is that we're not just talking about a domain that has elements taken from sets, for instance, right? But we are even talking about so-called lattices. And next, I want to teach you what a lattice actually is and why we actually need it also in particular in the setting where we do flow-sensitive static analysis. And that can be illustrated using, again, a very simple example that I'm showing you here. Let us assume that we are doing a certain kind of constant propagation where we are actually propagating concrete numeric values in a set. And let's assume we're doing that for such a simple procedure here, which is simply having a loop where it increments the value of x. Then, well, first we would propagate the value as it is, but then it would be incremented. And now at this point, we certainly know that given that x was 0 at this program point, it's now definitely 1. It cannot be anything else under this assumption that we had this value here previously, okay? Now we have to merge this here, right? So one branch is telling us x is 0, one branch is telling us x is 1. And now let's assume we are now doing a merge simply using set union over these right-hand sides. Then we will get basically this solution here. So this is now telling us x at this program point, we now know could be either 0 or 1. That is a new value we haven't seen before, so we have to process that particular statement again. We are applying its flow function. So this means we now definitely know at this program point here, the value can only be either 1 or 2. And now we are merging this again. And now you see what's happening, right? So again, we're doing a set union over these right-hand sides, and the set is growing again, right? So now we are assuming x can point to 0, 1, or 2. And again, this is being propagated to this branch here. And you can easily see this will continue forever, right? So if you implement such an analysis as it is here, by now I would say that's very naive, but when I got started with static analysis, I would certainly make these kinds of mistakes as well. Then you will get a non-terminating analysis because this continues running in a loop, right? You get larger and larger sets, and you find yourself stepping through this with a debugger, and you think, oh my God, where do these gigantic sets come from? And they're never being reduced, right? So you continue doing this until you run out of memory and your process crashes, and that's not a very satisfactory static analysis. So we want to do better than that. And the way we can do this is by inducing some certain ordering on the values that the analysis is allowed to compute, and by inducing also certain restrictions on what a merge operation can do and how it needs to adhere to this ordering. For that, we first need to define a very simple notion, which you have already very likely seen before. It's a so-called partial order. And a partial order is simply a binary relation between different elements. And here we write it in this manner. And it has three different properties. It's reflexive, it's transitive, and it's anti-symmetric. So what does this mean? First of all, if we assume that we have the ordering between these 5 elements that I'm showing you here, so this means we have an ordering between D1 and D2, for instance, then reflexivity means, so let's assume that each individual element here is a domain element, right? So each of these nodes here in this partial order would be, for instance, such a mapping here, right? Or any other kind of domain element that I showed you previously, right? So these are domain elements, and we assume they're ordered this way. So for instance, you could have a domain element here that is larger in the sense that it's a superset of the other one that you have here, okay? Now, if we talk about reflexivity, it basically means that implicitly every element is also in this order with itself, right? So that's what this definition here says. For every x in the set is ordered with itself. That's also why this is sort of denoted similar to a smaller equal sign and not just a strict smaller sign. Then we also have transitivity. So that means if we have such an ordering between D5 and D3 and D3 and D2, for instance, then implicitly we have this ordering edge as well. So D2 is also in the order with D5. And then we have anti-symmetry. So that means if you have an ordering, for instance, between D5 and D3 that's pointing in this direction, you are not allowed to also have an ordering in the other direction. Okay, that's a partial order. And you can find many natural examples of this, and many of them are typically also denoted similar to this notation that you see here. So for instance, you can have the smaller or equals ordering over the natural numbers, or you can have the subset or equals relationship over finite sets. That would all be partial orders. We can also look at another partial order that you see here. And this one is actually forming a lattice. And in a few slides, I will also formally defining what a lattice really is. This is a so-called sign lattice, and it's one of the most simple lattices you can think of. So let's assume here we are doing some kind of constant propagation over a program. But here we are no longer interested in the concrete number that a certain variable is holding, but we are only interested in saying whether this is a positive number or a negative number or zero. So the domain only carries these three different potential values, plus two extra values that we here call top and bottom. And these stand for the following. So top here is to say it could be any number. We don't know which one, but it's so the variable has been assigned a number, but we don't know anymore whether it's positive or negative or zero. And we can also have the bottom value, which means the variable has not yet been assigned a number. So this could be the case if the variable is still uninitialized at the beginning, for instance, or in case you have unreachable code that never assigns the variable a value because the code simply never actually executes, right? And now you could have a program analysis that arranges the domain values in such a way and that then actually assigns variables to individual elements of this sign lattice here, right, to this domain. And that then would give you such a very simple kind of constant propagation, or it's, in this case, it's actually called a sign analysis. And now, similarly to what we saw in typed systems, also here we can basically again generate constraints, right? So here we basically have one constraint per statement, or you can also more exactly say one constraint per control flow graph node. And if we now, for instance, assume that little program here where we have variables A and B that are initially uninitialized and where we have some unknown input value that is coming from the command line, for instance, then this would translate into such a control flow graph here. And we could now obtain such mappings like you see them here. For instance, at the beginning, we would say that A is being mapped to bottom and B is being mapped to bottom because we don't really know basically this hasn't been assigned a value, right? That's what bottom really stands for in our lattice. And we name this environment X1. Then here, after this statement, we would take this environment X1, but we would update it with the following mapping. We would say that now A is definitely holding a positive value, right? Because 42 is definitely positive. So we are replacing this initial mapping for A that we had here by this one. That's our new mapping X2, which after the third statement, we would update as follows. So here, now B is pointing to a new value, and whether that is positive or negative or zero depends on A, and it also depends on the input, right? And here we would basically say we are computing the value as such. So we are taking the value of A that we already have in the mapping X2. So that would actually resolve to this plus domain value here. And then we would compute sort of an abstract plus operation over this value. and the top value. And here we have to use top because the input value is really unknown. It's not just uninitialized. We don't really know what value it is. It could be anything. And that we would be able to statically compute, and that would then be the new mapping for B. Then similarly here, in order to compute the new value for A here, we would take the environment x3 from here. We would update it by using the value A that we had for A there and the value that we had for B there. And we would sort of conduct an abstract subtraction operation here. And that would give us the new value for this. And these operations here, plus and minus, they are really abstract operations. So they say things like the following. For instance, if you know for sure that your current value is 0 and you are adding something to it, then you now know for sure that you are going to have a positive value, right? If you already have a positive value and you're adding something to it, you know that again you're going to have a positive value. If you have a positive value and you subtract something from it, you don't know anything, right? So that would then actually be assigned top. And so these are abstract operations that you need to define that operate on these abstract domain values only. You can then have some loss of information. So for instance, like I just told you about, there are certain combinations that can lead you to top. So for instance, also if you're dividing even a positive number by another positive number, even that has to be assigned top. Because for instance, if you're dividing 1 by 2, then this is rounded down. So this would actually be the value 0. But it could only be the value. It could be the value 0 in this case, but you don't know the dividend and the divisor, right? So you don't really know whether it is going to be the case or not. So it could be 0, or it could also be a positive number. And in this particular lattice that I showed you here, let me actually go back. If we say it could be a positive number, or it could be the 0 value, then if we merge this to sort of the union of both, you could say, then this is actually being represented by top, that you can see by these lines here. So in this particular lattice, if we merge plus and 0, we end up at this top value. So this is the safe approximation basically of these two values. You can have lattices that have a somewhat better or richer precision. So for instance, here we have a somewhat extended lattice that has the following property. So if we merge 0 and plus here, we don't immediately merge it to top, but we merge it to some other fictional value, plus 0, which basically represents plus or 0, right? So it's really any positive number, possibly including 0. And similar here, we have a minus 0 as well. And you can always have richer lattices with better precision, but as we will see later, there are trade-offs between such lattices because often the larger your lattice is, the worse the performance of your analysis can also be. Now, what's important about lattices is that you can have so-called upper bounds, and they are actually important for termination. And that's what I want to talk about next. But before we go there, I will actually take a short break, and I'll get back to you with these and the follow-up topics in the next brief video. Thank you very much.